Welcome back to the this course on advanced manufacturing and process modeling. So, we were discussing about the welding section of the course. So, in the last class we have discussed about different welding processes. We have given an overview about different energy sources that is utilized for fusion welding. We have also briefly discussed about solid state welding processes. So, now we will discuss about the fusion welding processes which are arc based in this class in with detail, and we will start with explaining the mechanism. So, let us start with the this emission and ionization of electric arc, that is the intrinsic for the arc welding processes. So, what we do here, so if you see this schematic over here, so you can understand here that the work is a positive electrode, that is anode, and then the electrode is negative in charge. So, what happens when that negative electrodes is in contact with the workpiece anode. So, then there is a the contact is made, and then immediately when the electrode is withdrawn, as a result the metallic bridges start breaking, thus increasing the current density per bridge. So, finally, the current density rises to such a high value that the bridges starts boiling, and then the electron gets released from the both the workpiece, that is anode, and also from the cathode, but it is basically getting repulsed in case of electrons come out from both the surfaces, and the electrons having the negative charge coming out of the anode are pulled back, whereas those coming out of the electrode are also attracted towards the anode. So, the rate at which the electrons are emitted from a hot surface can be expressed by this equation, that is I is equal to c theta square exponential minus beta by theta. So, where I is the current in ampere per semi square, theta is the absolute temperature, c is a constant, and beta is given by phi e by k theta, where E is the charge of an electron, k is the Boltzmann's constant, and phi is the thermionic work function, so which is measured in electron volts. So, here in this table you can see the for different metals ionization potential and as well as the thermionic work function in electron volts are shown for some standard metals like aluminum, copper, iron, tungsten, etc. So, you can see that thermionic work function is much lesser in case of sodium and potassium, whereas it is very high in case of tungsten. Okay. So, and then to move on, so we can discuss about, so like for example, if we can assume the conductivity of the arc column to be independent of the arc length L, which can be clarified from this this graph which is shown above here. So, this is showing the potential across the arc space. So, here you can see that this is the arc column in between the anode space and the cathode space. So, in the x axis is the potential, that is the voltage applied, and this is the y axis, the arc space is shown. So, the electrode drops here are also independent of the arc length, hence we can write the voltage drop across the entire arc as V is equal to A plus BL, where V is basically the potential, the applied voltage. So, and in this figure, subsequent figure, which is showing the current voltage characteristic of an arc. So, you can see that two different characteristics of the power source. So, we can also discuss about the sharply drooping characteristics and also the flat characteristics later on. So, you can from this slide it is clear that that current voltage characteristic of an arc, that if you decrease the current in an arc, the if you increase the current, then the voltage drops up to a certain extent, and then there is a break even point where after that if you increase the current further. So, this is basically the break even point. After that if you increase the current further, so then there is a spike in the voltage again. So, here from this figure you can understand that so this is a case for the I mean flat characteristics between the current voltage in case of arc column, and also the sharply drooping characteristics which is marked by CD, and the flat characteristics is marked by AB. So, here you can see that in case of sharp characteristics, if there is a change in the arc length from L to increase in arc length from L to L plus delta L. So, then you can see if the current voltage characteristics is a flat one, that means if it follows the line AB. So, you can see that if because of the change in the I mean arc length, there is a significant change along in the current. So, you can see this much is the change in the current as shown by this I mean arrowed line, and then corresponding the change in voltage can be marked from here. So, you can see, so this is basically the change in voltage, that is if I drop a line from here and from here. So, you can understand this is the change in voltage in case of if the I mean current voltage characteristic is a flat one, whereas in case of sharply drooping characteristics, that is why this is the desired configuration that is followed in case of arc welding. So, you can see that if there is a change in the arc length again along this CD line from L to L plus delta L. So, you can see the change in current, I mean because of that, I mean basically current drops is very less, and also the change in voltage, that means spike in the voltage is comparatively lesser than what we have evidenced in case of I mean flat characteristics. So, more than the voltage, the change in I mean the current is much lesser in case of sharply drooping characteristics. So, that is why this is basically the preferred choice in case of arc weldings. I mean this is the preferred choice of voltage and current I mean relationship. So, that is why it is preferred. So, this is the brief about the arc source, and also you can see focus your attention here. You can see that so this is the relationship which is plotted between the arc power and the arc length. So, you can see that with the increasing arc length, there is a increase in arc power up to a certain break even point, that is termed as the optimum arc length. And then after that if the arc length is increasing further, so then you can see that there is a drop in the arc power. So, that is why this is the I mean optimum arc length, that is I mean of course, it depends upon the current voltage characteristics of the source, and also it varies across different welding processes. So, the target should always be that to remain in the optimum arc length, so that we can draw out maximum power for fusion welding of the materials that we are trying to execute. So, moving on, if we discuss about the chemical heat source, we have already discussed about the electrical source for power for welding, for fusion welding. So, in case of chemical heat source, that preferred example is acetylene C2H2, which is the most common chemical heat source and is used in a chemical gas flame. So, in the presence of excess oxygen, it burns according to this reaction which is shown over here. So, acetylene burns with oxygen, produces carbon dioxide and water, and it releases heat. So, basically it is an exothermic reaction, so which is termed here as delta H1. So, the amount of heat liberated here is 1.275 into 10 to the power 6 into 106 kilojoule per kg mole of acetylene. So, if oxygen is premixed with acetylene 1:1 mole ratio, then the combustion reaction can be like this, where C2H2 plus O2 generates carbon monoxide and then hydrogen, and also it liberates heat. So, again this is an exothermic reaction. So, where the delta H2 is much lesser than the initial if I term this reaction as 1 and term this reaction as 2. So, then the heat released in case of reaction 2 is much lesser than the heat released in case of reaction 1. So, and the carbon monoxide and the hydrogen produced later burn, producing the acetylene again. However, this heat, since it is generated over a large volume and at a lower temperature, does not add much to the welding process. So, the gap between delta H1 and delta H2 is 0.827 into 10 to the power 6 kilojoule per kg mole. So, This is about the chemical heat source. So, there, apart from acetylene, there is another popular chemical heat source, that is if we are using the combination of aluminium and Fe3O4 ferropheric oxide. So, you can see that they react and it generates elemental iron and also aluminium oxide Al2O3, and it liberates heat. Again it is an exothermic reaction. So, it liberates heat in the order of delta H is equal to 0.242 into 10 to the power 6 kilojoule per kg of atomic weight of the contained oxygen. So, the adiabatic temperature here is calculated to be in the order of 3000 degree centigrade. So, here the reaction is utilized in what is known as thermit welding. So, we will discuss about thermit welding in detail later in this section. However, for your knowledge, I can mention that thermit welding is a technique which is generally used for executing the welding in case of railway lines which are present in the remote locations where there is lack of electricity. So, we can still achieve the welding between the where there is need for the assembly or to correct any breakage or gaps in the railway tracks, which can be very much achieved by the thermit welding. So, we will move to the contact resistance heat source. So, again this is again a electrical heat source like in case of arc welding. However, the nature is different. Here the electrical resistance heating is considered as a heat source. So, this may be done either by utilizing the contact resistance of the interfaces or by utilizing the resistance of a molten flux and slug, that is called electro slag welding. So, let us focus our attention to the contact resistance based heating. There and doing the fusion welding thereby. So, you can see here. So, when the two metallic surfaces are brought into contact, not only a small fraction of the apparent area is in actual metal to metal contact. Why? Because for example, if you are talking about aluminium, then aluminium is very much prone to oxidation, even magnesium is very much prone to oxidation. So, then there is a oxide layer which is already present over the surface of the metal. So, that is why even if we are keeping both the plates in contact along their surfaces, there may not be the contact established at throughout the surface of those plates. Rather, there are locations where the oxide layer is not there. So, those are the locations where metal to metal contact can be established, which are shown over here. So, this is a contact point, this is another contact point. So, these are the contact points which are responsible for generation of tiny metallic bridges between the adjacent surfaces which are brought in contact to each other. So, the oxide layers in contact carry no current. So, that is why it is only those locations of contact which are responsible for transport of the electricity or the current. So, that is why the result as a result the current flow is constricted. So, this is the why constricted, because the current is only allowed to flow in the chosen point or the marked point where the metallic bridges are formed, where the metal to metal contact is established, not in other regions because of the presence of the oxide layer to its surface. So, that is why we are calling the current flow as constricted. So, due to this constriction, the resistance to the flow of current increases, and this increment is termed as contact resistance. So, an estimate of the order of magnitude of this resistance can be obtained by idealizing the constricted current flow. So, this is what shown in the figure below. You can see from the schematic again with the following assumptions. So, what are the assumptions? All bridges are of uniform size and spherical shaped ones with radius r1, and all bridges are uniformly spaced within the adjoining surfaces of the metal plates, and they are spaced at 2r2 distances from each other. And then the constriction effect due to each bridge is restricted with a concentric sphere of radius r2, and each bridge is of 0 resistance. So, these are the assumptions that we follow in case of contact resistance based fusion welding processes. Okay. So, while we move on, so now if there are n bridges per unit area, so then the contact resistance per unit area can be calculated from the resistance of each spherical constriction and considering n such paths in parallel. So, each spherical constriction consists of two identical hemispheres in series. So, the resistance of each hemispherical constriction is given by R is equal to small p R 2 minus R 1 into S divided by S. So, where P is the resistivity of the material, R 2 minus R 1 is the length of the current path, and S is the geometric mean area of the two hemispheres of radii R 2 and R 1 respectively. So, where from we are getting this radii? So, these are the locations. So, you can see this is the radii R 2 and here this is the bridge of radius R 1. Okay. So, I mean, so this is basically I mean the distance between the two bridges, you can see here it is R 2. So, from here to here it is R 2, again from here to here it is R 2. So, the total distance is 2 R 2. This is how we are getting the total distance between two adjacent bridges over the I mean surfaces which are in contact, and the radii of that individual bridges. So, this radii of these individual bridges is basically R 1. Okay. So, from here we are basically deriving this expression. So, where P is the resistivity of the material, R 2 minus R 1 is basically the length of the current path, and S is the geometric mean area of the two hemispheres of radii R 2 and R 1 respectively. So, thus S is equal to 2 root over 2 pi R square, I mean R 2 square into 2 pi R 1 square. So, which becomes equal to 2 pi R 1 R 2. So, substituting this value of S in the above equation, that is termed as equation 1, we can obtain the value of R. So, that is the resistance of each hemispherical constriction. So, how we can get it? So, you can see that R is equal to P R 2 minus R 1 and then divided by 2 pi R 1 R 2. Okay. So, that which becomes equivalent to rho by so here please correct it, it should be rho, it is mistakenly written as P. So, then rho R 2 minus R 1 by 2 pi R 1 R 2 can be approximated as rho by 2 pi R 1. Why we can do that? Because R 2 is much greater than R 1. So, hence the total constriction resistance per unit area is given by, because there are n such paths in parallel, R c is as 2 by n into rho by 2 pi R 1. So, then it becomes equal to rho by n pi R 1. Okay. So, this is the total constriction resistance per unit area. So, in the absence of the interface, the resistance of the same path is negligible. So, thus the contact resistance per unit area can be taken as that given by the above equation. So, experiments show that the assumptions leading to this above equation, which is termed here as equation 3. So, the do not cause an error more than 15%. So, the contact resistance per unit area can finally be taken as, considering this 15% error, we can express it as R c is equal to 0.85 of rho by n pi R 1. So, this is basically the final expression for the contact resistance considering the error involved for per unit area. Okay. So, now we will discuss about the heat flow characteristics. So, a study of heat flow characteristics can provide an estimate of the minimum heat input rate required to form a weld of a given width. So, in most cases the heat is liberated in a small zone which is idealized as a point source, and the heat flow from the source is 3-dimensional in nature, and in a few cases, that is in butt welding of relatively thin plates. So, as we have discussed several times earlier, again I am drawing for your ease of understanding. So, this is basically a typical butt welding of a single V groove butt welding process that I have drawn over here. So, this is the weld bead geometry over here. Okay. So, this is basically plate A and plate B, and then so the heat is liberated along a line and the heat source is idealized as a line source. So, in such situations, when the workpiece which are experiencing the fusion welding is of very thin size, then the heat flow can be along a line and it can the source can be termed as two dimensional in nature. So, in case of three dimensional heat source, that means in case of thick plates we can consider it the heat source as a point source. So, then the rate of heat input Q can be given by this expression, that is Q is equal to 5 by 4 pi w k theta m into 2 by 5 plus nu w by 4 alpha. And what are the individual notations? So, Q is the rate of heat input in watt, and w, small w here, small w is basically the width of the weld in meter, K is the thermal conductivity of the work material, watt per meter per degree centigrade or watt per meter Kelvin, as per whatever the unit is chosen, and theta m is the melting point of the workpiece that is experiencing the fusion welding process. So, above the initial temperature, that is the initial temperature when it is started, the welding process is started, and this V or nu is the speed of welding in meter per second. Okay. So, here the point source and line source attributes are shown, and then if we move ahead in and then we can define the two dimensional heat source. So, when we as I told you earlier that in this case the workpiece plates, workpiece material is having a lesser thickness, that means a thin plate which are experiencing fusion welding. In this case the welding heat source can be considered as a line source, and it can be considered in two dimensional in nature. So, in that case the heat input Q can be expressed as 8 k theta m H into 1 by 5 plus nu W by 4 alpha. So, here H is the plate thickness. Okay. So, in arc welding with short circuit metal transfer, the heat input rate is easily seen to be Q is equal to CVI. So, what is the, so this is the rate of heat input. So, Q and V is the applied voltage or arc voltage, I is the arc current in ampere, and C is the fraction of total time during which the arc is on. So, this is the distribution, time temperature distribution or variation of temperature with time at different distances from the welding heat source. So, it is quite easy to understand. So, you can see that as we are moving further from the heat source, so the temperature gets decreased. So, you can you can follow these lines 1, 2, 3, 4, which are more further and further from the heat source, which is located over here. So, you can see that the point which is most close to the heat source, there the maximum temperature, if we can draw a line over here. So, then we can see that the maximum temperature is say T max in case of curve 1 or point 1 is much higher than the T max of the point 4. So, this is because the distance or if we can mark it as T1 and mark it as T4, then T1 is much higher than T4 because of the proximity of point 1 with the welding heat source, and point 4 is further apart from the heat source. So, this, and also with time there is a decay in the temperature of the a weld zone where we are basically measuring the temperature. Again that is that is understandable, because with time the in case of fusion welding that melt pool is experiencing solidification and it loses its heat content because of releasing its heat to the ambience, and thereby going through the phase transformation process, that is liquid to solid transformation, that is generally happens in case of fusion welding process of metals. So, because of that the heat loss happens and the temperature drops. Okay. So, the three important effects intimately connected with the cooling of a fusion weld, what are they? Number 1 is contraction, number 2 is residual stress generation, and number 3 is metallurgical phase transformation. So, what about contraction? So, if you remember, I have discussed earlier also that assume this schematic. So, this is the case of a typical fusion weld. So, this is again the case of a butt weld along the edges of two plates. So you can see, so this resembles the like a casting which is done in a very big mold, and very localized melting and solidification happens in case of fusion welding process. So here, during the freezing of the weld pool, a decrease in the volume takes place, again because of the phase change process, because as you know that the density of the same material in liquid state is lesser than than the density at the solid state, because because of this, when there is phase change happens from the melt pool from liquid to solid state, there is a there is a contraction that takes place in this region of melt pool, and also it depends the effect of contraction and the amount of contraction also depends on the type of joint that is getting developed by the fusion welding technique, as also can be seen from these schematics also. So here the solidification front moves simultaneously from the bottom upwards and also from the sides inwards. So this is basically the direction. So as we all know, why it is moving this way, because the heat is getting extracted this way, that means out from the outward direction. So assume that this is basically the mold as we have discussed in case of casting. So assume that this is the mold wall in case of this region where a micro casting is happening between because in the weld pool. So then because the heat removal direction is this, so then opposite to the direction of heat removal, so the heat removal is happening outward from the melt pool boundary. So that is why the columnar grains grows inward from the melt pool boundary. So this is the direction of growth. Okay. And also because there you can see there at the bottom also, bottom section also serves like a wall only. So here from here the direction of heat removal is outward. So that is why there is a movement of the solidification front which is inward. So that is why simultaneously from sidewise and also from bottom to top, the solidification front moves in case of fusion welding. So further the molten top portion always makes up for the contraction in the inner layer. So you can see, focus this case. So here you can see this is basically the typical case of the risering effect that we have discussed in case of casting. So here the top layer compensates for the sintered shrinkage happens in the bottom layers, and thereby you can see the top layer is the layer which is solidifying at the last, and the shrinkage pipe mostly happens at the top. So you can this is the next step you can understand from here when it is completely frozen, and this is basically the shrinkage pipe which is forming if there is not proper feeding of the liquid melt in the weld pool. Okay. So that is a typical example which can originate, the kind of defect can originate in case of fusion welding processes if the joint design is not done appropriately. So further the molten top portion always makes up for the contraction in the inner layers, and piping occurs only in the surface layers. And then in case of figure B shows the solidification in a corner joint where more cold metal is near the surface of the weld pool, thus the top of the weld pool freezes faster and a long piping throughout the joint may occur. So this is the contrast between these two cases, because this is a corner joint. So that is why the melt which is kept at the top loses its superheat much faster than because of the proximity of, because it is a corner joint. So that is why here the pipe formation, the effect of shrinkage is more pronounced in case of corner joint compared to that in case of a joint along the edges. So that is why considering the location of the joint, the design of the joint and the melt pool, the filler metal requirement, if we are talking about the homogeneous or heterogeneous welding, so filler material requirement has to be estimated accordingly. Okay. So if we go ahead and now, so we can discuss about the residual stress. So you can understand here that this is basically the weld pool. If I draw the typical this butt joint again, so you can see, so this is basically the weld pool which is forming. So, basically as we have already discussed that weld pool want to contract, whereas this is the workpiece material which are experiencing fusion welding with each other, it does not let it to contract. So, then what happens? So, they basically provides a tensile pull to this, I mean that weld bead or the weld pool region which is trying to contract because of the phase transformation happening here, because of the liquid to solid transformation, I mean the freezing happens at the weld pool region. So, against this the contraction, the workpiece material applies the tensile stress over it, and simultaneously this contracting, I mean because based on Newton's rule we know that every action there is a equal and opposite reaction. So, the same principle applies over here. So, because of the, I mean tensile stress that is applied by the workpieces to the solidifying weld pool, the weld pool in return applies a compressive stress over the plates, I mean workpiece material which is undergoing the fusion welding process. So, that is why you can see that, I mean if we plot a stress versus distance plot over here, so then the stress changes sign. So, if we drop a so then what will happen, as we told that the residual stress which is generated in the weld bead is tensile in nature. So, then that is what happens over here. So, you can see that and then the solidifying weld bead exerts a compressive residual stress over the workpiece. So, in the workpiece till the melt pool boundary, it is the stress is compressive in nature. So, this is sigma stress and this is the distance, this is length. So, and then at the I mean weld pool, the solidified weld pool, the residual stress generated, it is tensile in nature. So, this is minus, this is plus, and again when it crosses the boundary of the solidified weld pool, again in the when it enters the workpiece, then the stress again is compressive in nature. So, this is the I mean case of residual stresses, and this is also the region because of which there is the distortion that happens in case of weld joint if the joint is not designed properly, and if it is not I mean designed with a I mean appropriate measures to counter the distortion, it can happen that the post welding that significant distortion may occur because of the residual stress generated in the joint and also in the workpiece material. So, this residual stress may also result in the cracking in case if we are talking about welding of brittle materials, and it is not important, not so much important if we are talking about a ductile material. I mean fusion welding of ductile material. So, now if we focus onto the metallurgical changes, so these changes happens due to the heating and subsequent cooling of the weld and the heat affected zones of the parent material. So, such changes significantly affects the quality of the weld. So, the weld I mean wide variety of changes that may happen depend on various factors like the nature of the material, that is whether it is single phase or two phase, the nature of the prior heat treatment, whether the workpiece has undergone heat treatment or not, and the nature of the prior cold working, that means whether the workpiece is a cast one or it is a cold worked one. So, then all those things decides the metallurgical changes that takes place in the weld zone, that means where the weld pool is formed, and also the nearby zones, that is the HAZ heat affected zone, and also I mean beyond that. So, here when we are talking about the characteristics of a welded joint, fusion welded joint in case of a pure metal. So, you can see this is basically the region where the melt pool has been formed. So, this is the region of melt pool, and then this is the melt pool boundary. So, you can see I mean, so this is basically this is the region where the rapid solidification takes place, I mean post I mean melt pool formation, and I mean so that is why I mean beyond that there are some coarse grains which are I mean experiencing, which are happening because of the I mean the heat, because of the heat that is generated in the weld zone. So, if we drop the lines from here, it will be clear. So, because of the heat generated, so this is basically the heat affected zone HAZ, if I increase the size. So, this is basically this is the zone where the weld pool has formed, and this is the region what is called HAZ, heat affected zone, and this is basically beyond that the base metal. So, you can see from here that the I mean that in case of heat affected zone, because of the heat it is experiencing due to the welding heat source, the grains got elongated, and that is why here the ductility is increasing. And then when the heat affected zone is over, and then we are entering into the cold worked region, the original cold worked workpiece, you can see the ductility drops. The reverse trend has been observed in case of strength, because in case of cold worked material, as we know, that grain size will be much finer. So, because of that the strength is higher. However, the strength is very less in case of the at the middle of the melt pool, because of the rapid transformation. Also it can happen sometimes because of the defect formation which takes place, and then it increases, it undergoes a transformation from the center of the melt pool to the zone where it is entering into the original workpiece material. So, and so there is a so there is a maxima when of ductility when it is entering into the heat affected zone, heat affected zone boundary in case of ductility, and there you can see, although it is not a minima, but still this is the region beyond which the strength increase happens significantly till it enters into the original microstructure of the workpiece, cold worked workpiece, which is getting experiencing fusion welding processes. So, it is largely different when we are talking about a alloy. So, characteristics of weld joint in case of a precipitation hardened alloy. For example, if we are talking about aluminum copper alloys, so then these are precipitation hardenable because of the precipitate that generally forms, which are Al to Cu. So, you can see here. So, here if we again drop, so here we have drawn from the central line of the weld pool. So, from here you can see that when we are entering into the zone that is immediately towards the boundary of the melt pool. So, you can see which is the region which is precipitation hardened, very fine precipitates came out during solidification of the weld pool, which is towards the boundary because of the higher heat transfer at the boundary. So, then this region is precipitation hardened, and there you can see the strength is much higher, and then again it is strength gets dipped, experiences dipping at the heat affected zone, which is also as the you can see that over-edged microstructure because I already told that it is a precipitation hardenable alloy. So, these precipitates which are already present in the workpiece material, so then they experience coarsening because of the prolonged exposure to the heat generated by the welding heat source because of the weld pool formation. So, it is a prolonged heat treatment, the over-edged structure decreases the strength significantly, and then again it increases when it enters into the base material, the original workpiece, which is precipitation hardened, which is heat treated, quenched and edged structure, original workpiece metal. So, again strength increases. So, you can see that ductility follows the reverse trend at the over-edged zone, where you can see there is a drop in strength, you can see there is a significant increase in ductility, you can see a maxima of ductility in that over-edged zone, and then again the ductility drops when it is entering into the precipitation hardened workpiece material. So, with this I am finishing for this class, and then we will discuss further in the next class about welding joint design and the different kind of forces it withstands, it experiences, and how to design for that for different kind of welds, for example fillet weld or eccentric weld, etc. So, till then bye for now. Okay.